and therefore we are interested to study what is this material and how we can deal with the microstructures of this material. For example, now this is a typical composition of such a soft magnet where elements like silicon, boron, niobium, and copper are intentionally added in this proportion. So imagine that copper is only 1 atomic % present inside this material, intentionally added for the purpose. So the purpose is like this, that the physics of nanocrystalline materials indicates that when you now produce these kind of materials in a grain size of millimeter, then you can have the lowest possible coercivity. But if you now lie in a range between millimeter to micrometer, the coercivity increases dramatically. That means this cannot be a soft magnetic material with high efficiency. But on the other hand, if you now get into the nanometer regime, that means you try to reduce the grain size of this combination of elements in the range of, for example, 10 nanometer till 5 nanometer. The grain size, as it decreases, the coercivity decreases to the rate of 10^6. That means for each nanometer decrease in a grain size, you can have 10^6 times decrease in coercivity, which is therefore going into the soft magnetic regime again and making this more attractive. So in order to now produce on an industrial scale, a nanomaterial having a grain size of 5 to 10 nanometer, that means we really require a fine nanocrystalline grains. And this can be achieved by two methods. One, if you now add these kind of elements like niobium, copper, and boron, you can make this material in the form of an amorphous metallic glass. And then you try to conventionally anneal them for a temperature window which is slightly lower. For a time of half an hour to 1 hour, you can now produce nanocrystals in the range of 10 to 15 nanometer. But you can do the same thing by accelerating the nucleation process, by increasing the heating rate. That means at a higher temperature for a shorter duration of 4 to 10 seconds, you can also do the nanocrystalline even. And this is one setup we developed earlier, where we want to do this rapid heating with very high heating rate, holding it for a very short time. And because, as you see, the material is in this form of a ribbon, which is a metallic ribbon. So the thickness is somewhere in the range of microns with the width of 3 to 6 millimeter. We will now be able to have a very fast cooling rate as well. And therefore, you can now make this entire process of rapid heating in a continuous way. That means you can produce the ribbons, push the ribbons through the furnace, and you have a pulley with a certain tensile stress. You can now pull this material out of this continuous pool of ribbon. That means you can now anneal them, apply the magnetic field while it is annealing. You can apply also tensile stress when it is annealing, and therefore you can do a reel-to-reel processing of these thin metallic ribbons. But when you do this reel-to-reel processing at a high heating rate passing through a furnace, we are now creating microstructure which is in the nanometer regime because it has to fill within this range of limited coercivity. Now imagine that this material is in the as prepared condition. That means it is in the original amorphous state. If you look at the amorphous microstructure or the distribution of elements in the amorphous state in 3 dimensions, all the atoms looks randomly distributed. But in the application, we need to have defined nanocrystals from this random distribution, and therefore we need to generate nanocrystals by one of these annealing methods. Now, in an ideal scenario, in an application when this material is used, it is the curiosity is always to know what is this 1 atomic % copper doing. What happens if you do not have 1 atomic % copper? So in usual microscopy, if you go with 1 atomic % copper, it's even difficult to quantify this 1 atomic %. Forget about where they are present. But now we take this material in the annealed state to atom probe tomography. Now you can see this 1 atomic % copper translates in the form of the nanoscale clusters. If you see the length scale, these are all roughly in the range of 3 to 5 nanometers in diameter. And they are spatially distributed in 3-dimensional space. Now these clusters of copper induce what is called the soft magnetic iron 3 silicon nanocrystallization, and the remaining boron and niobium therefore gets concentrated in certain locations, which are therefore the amorphous stabilizing matrix of this material. So therefore, typical application will have this material in the form of 70 to 80% crystalline fraction and 20% of amorphous fraction, which is rich in boron and niobium. And that fraction of crystals determines what is the soft magnetic property that we get. And it all depends on how this copper cluster of 1 atomic % forms the clusters and how they enable in nucleation of this iron and silicon soft magnetic nanocrystals. Now, to understand the mechanism of this nucleation process, we embarked on looking into what happens if you rapidly anneal this material from the as prepared amorphous state till a reasonably mature state of 745 degrees. If you look into the X-ray diffraction, it indicates that somewhere in the range of 555 degrees, there is a first hint of iron 3 silicon nanocrystal formation from the peak broadening. And if you increase the temperature further until 695, it is only the iron 3 silicon crystals that are present, which has the DO3 structure. And if you increase the temperature to 745, there are other phases of borides that are going to form. And therefore, when the boride forms, the material loses its soft magnetic behavior because these borides are hard magnetic phases. So now if you look into this 535-degree annealed condition in a transmission electron microscope, as the XRD suggests being in an amorphous state, the diffraction pattern indicates here that everything is in an amorphous state and there are only this amorphous fringe contrast visible and no discernible crystalline contrast. Now the material annealed at 555 degree is looked into a transmission electron microscope. And you can see a lot of these grains in a bright field TEM, bright and dark contrast. If we do a diffraction pattern, then you can say from the position of the atomic planes, you can measure them and then you can say this is the DO3 structured iron 3 silicon crystal. If you want to see one of the crystal magnified, you can zoom in with high resolution imaging. You can see the grain size that we get at 555 degrees is 7 nanometers of iron 3 silicon and the rest amorphous matrix. Now you see that there's an amorphous matrix everywhere, and then these crystals are present in 5 to 7 nanometers. So now you go further because from this microstructure, it is impossible to know where the copper is present or what the copper is actually doing as a function of temperature. You only know that there is an iron 3 silicon crystal forming after 535, and at 555 you can see them. Remember this 535 where the transmission electron microscope indicates everything is going to be amorphous. Let us see what is happening with the copper cluster. So you go into atom probe tomography, and then now I filtered out only the copper distribution from the atom probe, whereas iron and others are still there. So if you look at the as prepared amorphous state, all the copper atoms are homogeneously distributed in a three-dimensional matrix. So now you anneal them at 535, as you saw in the earlier slide, where everything looks amorphous as per TM. You see the copper has already started forming these clusters in the nanoscale, which are now uniformly distributed across the three-dimensional space. Now you keep on increasing the temperature. The size of the copper cluster increases with increasing temperature with decreasing in number density. You can go to high temperatures. Now you can see at 745 where there are iron borides that are being formed, where the copper cluster now looks a reasonably big form of a precipitate of 50 nanometer in dimension, starting from 3 to 5 nanometer. So that means there is a continuous coarsening process happening as a function of temperature, increasing in size, decreasing in number density, leading to this particular process of coarsening. If you now want to understand how this coarsening is related with the nanocrystal evolution, we can summarize this observation in the form of a variation number density versus the volume fraction. You can see that copper cluster size increases with increasing in temperature and the number density decreases with decreasing temperature. So this size variation with number density, you can now split into three different stages. That means the stage one, where as per the XRD and TM, that everything was looking amorphous until 550 degrees, we had the highest number density of copper clusters. In the stage two, where we saw 7 to 10 nanometer of iron 3 silicon crystals, the number density of copper clusters already started decreasing and the size is already started increasing. So when we have the stage 3, which is 745 degrees, where iron borides have formed, leaving the material being hard magnetic, you can see that the number density is almost decreased. Only very few big precipitates are present in the size range of 10 to 15 nanometers. So therefore, now to understand what is happening in stage 1 and happening in stage 3, we can now look into the case of 535, where we have the maximum number density of copper clusters. You can now discretize this data set in a smaller volume. Try to distinguish the copper atoms that are part of the cluster and the copper atoms that are in the isolated three-dimensional space. Now, if you freeze this and look in a certain location, you can see that there are similar size copper clusters which are interconnected with each other, where you see this kind of a necking. Now you can take out only this little nanoscale region and zoom in further for their atomic distribution. And now you can see there is a bigger cluster which is in the nearest vicinity, but there are similar size clusters which are trying to coagulate or forming a neck between them. That means you can now see this in 3 dimensions. Two similar size clusters are trying to coarsen. The bigger size cluster stays away, smaller size cluster also stays away. And you can also quantify this concentration at the necking region by having a one-dimensional concentration profile passing through the two clusters along the interface. Now you can see the copper content is more compared to that of the matrix region, which is away from the clusters. Now looking into this way of coagulation that is happening in an amorphous matrix, you can say this is the coagulation necking and coarsening mechanism that is active when in the initial stages of clustering that is happening, because we anyway know these clusters are coarsening as a function of time, but the mechanism of coarsening you can study as a function of the overall microstructure of the material. Now in the amorphous state, you see that it is now coagulating, necking, and then coarsening. Now, if you take the same thing with the stage 3, discretize the data set based on the chemical identity, that means we can now identify the iron silicon crystals because we know anything beyond 555 degrees. We are now seeing iron silicon nanocrystals. You can now discretize these crystals based on their stoichiometry. That means 20% silicon, 80% iron, can identify which are those regions that are nanocrystalline. You can again see the copper with 3 atomic percent copper because the matrix is less than 1 atomic percent. The remaining matrix, which is an amorphous, which is rich in boron and niobium, in the blue color and the orange can all be nicely discretized. Now again, you can get a concentration profile that indicates these three different regions based on their chemistry. So iron silicon crystal having the DO3 structure, that means iron 2 silicon in a stoichiometry of 3:1. Then you have a copper cluster and an amorphous matrix that is rich in niobium and boron. So now in this state, between each copper cluster, you can now see more than one iron silicon crystal being present. That means there is no longer coagulation of copper clusters that's going to be possible because the iron silicon crystals will separate each of these copper clusters one from the other, and therefore the only mechanism of growth that is going to be possible in this case is the classical Oswald ripening of dissolving these clusters and then diffusing the copper through the matrix, reaching the next nearest cluster by the size variation. That means the bigger cluster tries to now dissolve the smaller cluster which are far away, and these copper atoms diffuse through the distance and then coarsen these bigger clusters. Now, if you try to understand that, imagine that there is no atom probe in three-dimensional space. If you try to see the same copper clusters which are now clearly visible in 3 dimensions in the projection geometry of a transmission electron microscope, even in the highest resolution STEM imaging we had of, you can see there is some concentration that is, or some intensity variation that is visible. If you try to map with atomic scale chemistry, atomic scale EDS, you can now see a lot of these copper in these regions visible. But this is no longer equivalent to what you saw in a three-dimensional space. And anyway, you try to overlap this copper concentration or copper mapping with respect to the crystallographic structure, then you can see that there is a crystal here of iron silicon. There are multiple copper clusters in a projected geometry surrounding these crystals, but there is no clear distinction of whether one copper cluster is in an interface relationship with the iron silicon crystal that is present inside. It is very hard to see from a transmission electron microscope. So now this means when you are unable to see these clusters clearly in 3 dimensions, how do we now relate whether all of these copper clusters, what you see here, are they crystalline or are they amorphous? So then again, we go back to atom probe tomography. To an extent, we can do what is called cluster crystallography. That means we can take one copper cluster out of this annealed condition where there are hundreds of clusters visualized earlier. And for this one particular cluster, we can now do what is called a spatial distribution map along the direction that you see now. And in the spatial distribution map, there is no correlation visible between these multiple layers that are present inside. And therefore, this stage 1 of a copper cluster, which is 535 degrees for short time annealing, represents an amorphous state of clustering. Now you go to the stage 2 condition or stage 3, take the one isolated copper cluster. Now again, you do the spatial distribution mapping. Now you see there is a correlation between each layer that is being analyzed, and the distance between the two different layers is 2 angstrom. If you now assume an orientation of 111 of a face-centered cubic structure copper with the 2 angstrom spacing between each interplanar spacing that is present, you can then say the lattice parameter of this little copper cluster of possibly 5 to 6 nanometer is in the range of 3.6 angstrom. So this way, you can now discern what is the crystallographic nature of the copper cluster present inside. The other way to verify exactly the same information is to take this same atom probe tomography sample into what is called the field ion microscope. That means you take this atom probe tomography sample with this copper cluster, iron silicon crystallite as represented as white color, and the remaining amorphous matrix of boron and niobium being imaged as I showed in the very beginning of the earlier lecture, that we can introduce gas species and try to image the surface atoms and see these crystallographic poles present inside, by which you can now identify that these crystals, which are very much in the apex region of the tip, are these nanocrystals of iron and silicon. And you can now notice these crystallographic poles present. By looking into the crystallographic poles, you can now identify the orientation of the poles by superimposing this detector event histogram over a stereographic projection. That means when you now try to superimpose a detector event onto a stereographic projection and looking into the polar structure here, you can now say that each pole can be identified with their Miller indices of HKL planes, and therefore we can now identify whether this particular cluster or a feature of crystalline nature that you see, is it now going to be crystalline or amorphous. So all of this information to a large extent can be therefore related for the crystallography as well. And the same field ion microscope can be extended to measure what is called the grain size of these nanocrystals by looking into the number of rings that are disappearing over a period of time and measure the nanocrystal size also. So therefore, this method enables you to identify the phases present, the orientation determined using the stereographic projection overlay, and the crystallite size can also be determined. So that means three-dimensionally you can visualize, you can get the crystallography. If you combine atom probe tomography with field ion microscopy, then you can get the phase identification, orientation determination, as well as precise crystallite size measurement at the nanometer scale. That is all possible. So I hope this gives you a broader idea of how atom probe is absolutely crucial compared to other characterization methods if you want to see nanocrystalline features clearly identified. Now, another example of where this atom probe tomography has been required or utilized to study what is called a self-healing material. Okay, so now to introduce a self-healing material, there is a material called max phase. Now, what is this max phase? A typical max phase consists of a fixed stoichiometric compound where the M stands for early transition metal, A stands for an A group element, and X stands for carbon or nitrogen. Now, when you have these three elements in this fixed proportion, you will now be able to create a nano-laminated microstructure. That means elements of early transition metal together with the element of X, which is carbon nitrogen, form a stronger bonding, which is a ceramic layer intertwined by a layer element, that is, it can be aluminum or silicon. So that means a layer of A is formed between two such ceramic layer. That means you will now be able to get a unique combination of especially dissolved lattice arrangement where M and X are together and A is in the nano-laminated form. Now, if the stoichiometry is wrong, you may end up getting a disordered carbide. That means the same single unit cell is now disordered in three different unit cells. But if you are in the stoichiometric range of the max phase, you can get a single unit cell which is so large, and you can see the M and X together and A as an isolated layer. The benefit of having this kind of a max phase, having this nano-laminated arrangement, is that this material will exhibit now a unique combination of properties or unique set of properties, that it exhibits both metallic as well as ceramic characteristic. The metallic characteristic stems from the A layer, which is purely metallic, and the ceramic characteristic because there is an MX kind of a bonding that is happening inside. So some of the unique combination properties are high electrical conductivity and thermal conductivity, high thermal stability and stiffness, and high oxidation resistance. So in the case of an example that I am going to show now, we are going to talk about oxidation resistance of these max phase coatings, which is therefore called a self-healing property. So now imagine that an aircraft which is flying at a very high altitude, which is experiencing a cryogenic condition, suddenly lands in a desert atmosphere, which is in the range of 40 degrees. So coming from minus 50 degrees to 40 degrees, there is a huge thermal transition together with the sand particles in the desert atmosphere bombarding these turbine blades or the propeller blades that you see. Now, at the edge of the propeller blade, when these particles hit together with thermal history, you can now have an initiation of a crack on the surface of this blade. Now, imagine a condition where you do not have any coating but the raw blade that is being exposed. This means A crack can initiate on the surface and it can propagate continuously because there is no arresting mechanism for the crack propagation because this propeller blade is rotating all the time. Now imagine if we have a coating of a max phase, which is the chromium 2 aluminum carbide. That means a max phase stoichiometry of 2:1:1. Now if this material exhibits a property of oxidation, that means you can have the coating and the moment the crack that is formed, if you know either heat or because of the in situ thermal treatment, that means coming from cryogenic to a high temperature condition, the A layer, which is the freely available layer of aluminum, can now react with the surface oxidation because you have a free surface opening by crack formation. The aluminum can react with the oxygen because they have a very strong affinity, and immediately it can start forming an alumina coating, which is now going to form in situ and cover up for the crack that is being introduced on the surface. This means you can now quickly fill up the crack in situ without any external treatment and avoiding the catastrophic failure of this particular propeller blade to fail because of the drastic crack propagation. So these things can be therefore improved by having this kind of a self-healing max coating. Now, where do we understand the requirement of microstructure as well as the nanoscale features present? So imagine a condition where there is a max phase that is being developed, but the crack propagation is very fast. So we want a very high kinetics. That means we want very quick rate of crack healing. That means self-healing has to happen at very fast. So to accelerate the kinetics of aluminum coming out of the material, out of the nanoscale coating, and then oxidizing on the surface, then we need to have a very high capability of aluminum diffusing out to the surface. So therefore, we added a silicon concentration of 0.7%. So which is again an A group element. So that we assume that we aluminum comes out, silicon substitutes aluminum to stabilize the max phase without any deficiency, while the aluminum can react with oxygen form an oxide as you see. The same oxide bright contrast is now shown separately for better visualization. Now all of these oxide grains in situ formed, in this case oxidation of the coating at 1120 degrees for 4 hours. You can see the nanostructured oxide scale has formed on the surface. But what you suddenly see is that in the presence of silicon, there is no grain growth of max phase. That means the width of the columnar grains did not increase. Whereas in the absence of silicon, you can see the width of the grains have dramatically increased and all the dislocations are visible. Then you get a slightly smaller or a 40% enhanced layer thickness in of the max phase of alumina when there is silicon. And when you do not have silicon, there is a coarser grain size of alumina grains that are formed and compared to finer grain size when there is 0.7 atomic percent of silicon added to it. This means if you now have a crack with 40% higher layer thickness in the case of silicon added alloy, we will now be able to get a completely filled crack region compared to partly filled crack region in the case of the max phase without silicon. Now the question is, there is a faster self-healing rate in the presence of silicon. Now where is the silicon going? What is it silicon doing? And why this is crucial? Because the self-healing property now completely seems to depend on silicon. And therefore, to understand the silicon role on the self-healing process, we embarked on the combinatorial synthesis. That means we now produced a series of alloys at a series of coatings at the same time. So these are the arrangement of substrate in a combinatorial synthesis setup. Now across this substrate, we now have varying level of silicon content. That means we use a target to produce a coating where one side of the target is made of chromium aluminum carbide, the other side is made of chromium silicon carbide. That means the bottom half is silicon rich, top half is aluminum rich, and in between you have a gradient of composition with varying silicon ratio. So this is something represented by this color coding. Now, if you try to get all of these materials annealed at 1120 degrees for 30 minutes in oxidizing atmosphere, then try to measure what is the scale thickness that is formed. That means what is the alumina layer thickness that is formed on the surface of this coating after we try to oxidize them under this temperature and time. So now you see with varying silicon content from 0% silicon until 1.5% of silicon into the max phase. You can see now the oxide scale thickness increases with increasing silicon content. That means you can see the microstructure. This is oxide scale thickness. So at 0.3% silicon, we see the layer thickness is more than what you can have when it is a silicon-free alloy. At 0.6% thickness, 0.6% silicon, the layer thickness increases further. It further increases until 1 atomic percent of silicon. And if you increase 1 atomic percent silicon, the layer thickness seems to decrease. So that means by using this method, you can now identify the maximum silicon content that can be added into the alloy to have the highest rate of self-healing is going to be 1 atomic percent. So therefore, we now realize the range of silicon content required for faster self-healing. So we now try to understand the case between 0.7% of silicon and 0% of silicon, try to understand what has happened to the material. And similarly, now you can look into the XRD of varying silicon content, and you can see that it's a single max phase with all the silicon addition until the silicon exceeded 1.5 atomic percent, where you can try to see the chromium silicon carbide trying to form with more and more silicon content. Now you looked at in TM without silicon, there are all columnar grains. The diffraction pattern indicates that it's a single phase max phase. Then you take this 0.7 atomic percent silicon alloy, then again the columnar grains are visible, and the diffraction pattern again indicates these are single phase max phase without indication of any nanoscale phases present inside because the grains are already nanocrystalline. Now if you take the same thing and you compare the grain size, you see that between 0% silicon and 0.7% silicon, there is a minor refinement of grain size. That means you can see 0.53 micron is a grain size that you can get with 0.7% of silicon. But where is the silicon? We do not know. Now you take one of these samples and go into high resolution TM microscopy. That means this little region we try to magnify using a STEM image. Now you can see in that particular region, some V-shaped uncharacteristic defect features are visible. So this V-shaped characteristic features now try to map with chemical mapping. And you can see all the elements of the max phase chromium, aluminum, carbon, oxygen are present inside, and they are uniformly distributed. Now take the case of the 0.7 silicon containing alloy and try to do the same thing. Now zoom in from one of these regions, try to see in a high resolution STEM mode. And again, you see the V-shaped features even in the 0.7 silicon added max phase. Now if you do the chemical mapping, then suddenly you see that there is a V-shaped arrangement of silicon atoms present inside this max phase, whereas all the other elements are uniformly distributed. So now suddenly you realize that the silicon is not uniformly distributed across the entire volume. Rather, they are located along this uncharacteristic V-shaped defects which are present along the growth direction of the max phase thin film. So now you try to see them in 3 dimensions because there is nothing much you can do beyond this limit of STEM EDS. So you take this into atom probe, you prepare the sample in the form of a needle, then you can see in a HADF image that there is a lighter contrast visible at periodic location, which is resembling the V-shaped morphology as you've seen before. And this needle, if you chemically map, you can suddenly see along this light contrast, you have a very strong silicon segregation. So that means it is not a 2-dimensional or 1-dimensional segregation. It rather looks like a 3-dimensional segregation of silicon, which is strongly visualized in this atom probe tomography needle. The same needle, if you now put into atom probe, now this is what you're going to see for silicon distribution. So suddenly we realize there is a 3-dimensional distribution of silicon atoms, but there are local regions where the silicon is now looking to be in the form of long elongated precipitates of the thickness of probably 30 to 50 nanometer, but with varying spacing. So you can now freeze this particular silicon distribution and try to evolve a surface around this varying thicknesses of silicon rich regions. And we can now try to quantify what is the difference between the broader silicon rich region of number 1 with the thinner silicon rich region of number 2. So you make a concentration profile, then suddenly you see that at the core of this precipitate 1, we get a chromium silicon carbide stoichiometry. And if you look into a thinner lamellar structure of silicon enrichment in number 2, we are now able to see a chromium 3 silicon stoichiometry. That means even at the nanometer scale, there is a heterogeneity which is unable to be seen in a TM, whereas in an atom probe in 3-dimensional space, we can now distinguish the morphological difference between the different silicon enrichments. And by looking into the quantified concentration values, we can now see there are 2 different types of silicon enrichment. One is chromium 3 silicon, the other is chromium silicon carbide. Now, if you try to see whether these phases are realistically possible, we can now look into the phase diagram of varying silicon content. So we prepare this material at 600 degrees of sputtering. So at that particular condition, the chromium 3 silicon stoichiometry is certainly possible in addition to the max phase stoichiometry. Now you try to anneal the same thing at 1120 degrees as what we have seen in an oxygen atmosphere. Then are we now expecting the silicon to be present inside? So that is something we need to verify. So we now oxidize this material. Again, we try to get the oxide that is formed here in a much faster rate because of the presence of silicon. Now, what is silicon doing to increase the oxide layer thickness with finer grain size of oxide? If you now look into a TM again, we can see along the grain boundaries after oxidation, there are these particles that are going to be visible, which are in the nanometer scale. The chemical mapping certainly indicates that there is a particle sitting on a grain boundary of columnar max phase, which is now rich in silicon. If we now try to examine what is the silicon enrichment, if you take a one-dimensional profile, then you can see that the max phase still has some amount of silicon which is present on the V-shaped defect before oxidation. But after annealing leading to oxidation, the V-shaped segregated silicon has now coarsened into a type of a chromium silicon precipitate. It's no longer elongated as in the as deposited condition of an atom probe that you have seen, but now it's more like a globular precipitate of chromium silicon enrichment. And now from the stoichiometry, you can say this is again a chromium 3 silicon stoichiometric precipitate that is sitting on a grain boundary. But how do we now statistically know which of these precipitates are chromium silicon carbide? So therefore, we embarked on a study where we introduced a new method called transmission Kikuchi diffraction. The same TM lamella, the same volume or area of analysis is now subjected to diffraction so that you can now get the orientation distribution of all the grains in the max phase present inside with the carbide with the oxide. You can now identify their orientation. You can also do the phase mapping. But when you do the phase mapping, you can certainly see based on the crystallography that there is a chromium silicide, which is different crystal structure compared to which is a cubic crystal structure compared to the alumina, which is the hexagonal crystal structure. So that some oxygen has diffused along the grain boundary, forming an alumina inside the max phase, whereas the silicon has all now formed a chromium silicon precipitate. The aluminum that has went out to react with oxygen has formed an alumina on the surface coating, and in between there's a depleted region where we can now form a chromium carbide. That means by connecting the same TM sample with these methods of diffraction, we'll now be able to correlate crystallography with the localized chemistry. Now, further, if you now look into the sample, and at that annealed condition, if you magnify this, you can see there are tiny nanoscale precipitates present in a specified direction across this entire lamellar volume. Now, what are these precipitates? Because TM, if you now again do the chemical mapping, there is nothing that you can identify whether these little precipitates that you see here along this region are they enriched with something, because all elements are now clearly depleted out of this region, so which typically may indicate that there is no material present in it, or there is a void, or there is a halo. Now, the same thing, if we now looked into the atom probe, suddenly you see that with 0.3% silicon in an annealed condition, there are a lot of these nanoscale precipitates where the length scale matches exactly with that of a TM image, whereas they are aligned in certain specific directions. So you can now align them and orient them in order to see their arrangement in specific direction with respect to the directionality in the TM image. Suddenly you realize there is an aluminum enriched precipitate that is present along the specific directions together with the oxygen. That means we have an oxide that is formed together with the silicide and together with the max phase that are being visualized. So all these oxides now are possible to be seen only in nanoprobe, whereas in TM by chemical analysis, you can see there was nothing segregated, so it looked like more or less like a void. So if you connect all of these things and try to understand why are we able to see the precipitates present but in the form of a void in a TM, whereas in an atom probe we see a realistic volume of 3-dimensional nanoscale precipitate. That means in the sample preparation, we can also introduce what is called a Fib-induced damage, where if you now look into the as deposited condition, we saw the V-shaped defects across the lamella and the silicon segregation across them, but we could not really see them as precipitate because along the grain boundaries, there could be the Fib-induced preferential milling away of these silicon-rich precipitates which are protruding on the sample. And similarly, when you anneal them, all of these elongated chromium silicide precipitates are now turned up into a globular precipitate, much bigger in size, but still within the nanometer range. But none of them could be resolved unless we went into looking into the atomic distribution of silicon. Now, all of these grain boundaries might have had these precipitate structures, but because of sample preparation, they were all disappeared. And similarly is the case of the 0.3% silicon annealed sample or oxidized sample. A lot of these precipitates were visible oriented along the columnar growth direction, whereas TM was unable to show the realistic presence of any precipitates by chemical mapping. Whereas in a NANO probe, you can now see all the aligned aluminum-rich oxides being present, which are exactly following the length scale in terms of size as well as along the orientation. So you can now get a comprehensive nanoscale analysis when we try to do this atom probe tomography. Now, the further significance, in addition to identifying these nanoscale precipitates, is how are these aluminum now diffusing to the surface, leading to the process of self-healing. That means if you want to understand from the ash deposited case, how do the aluminum go to react with oxygen when you anneal at 1100 degrees, for example. So if you now look into the grain boundaries, which is this particular region magnified here, you can see there is a white contrast, which is predominantly visible, which is not visible here. That means there are more elements that are trying to come out of a specific type along the grain boundary. That means you can now measure the average oxide layer thickness of 19 nanometer, which is this thickness that you see here, where there is an enrichment of aluminum. If you're now trying to see for the same thing for the case of silicon added alloy, if we now look into the grain boundary, there is a much more stronger enrichment visible, much more thicker region visible compared to the silicon absent alloy. That means you can zoom in. Now you can see for the same zoom in condition, the average oxide layer thickness is 43 nanometer. That means this region is thicker, twice thicker than what you see in the case of without silicon alloy, and therefore silicon is enabling in aluminum going through the grain boundaries of columnar grains of a thin film and then forming these much thicker nanoscale oxide layer on the surface, which is responsible for self-healing. That means it is enabling diffusion of aluminum at a much faster rate. If we now summarize all of these together, by combining the information that we got from ADA probe, combining the information that we got from TM, now you can see we have V-shaped defects in the as prepared thin film, which has nanocrystalline grains, and in the without silicon case, the V-shaped defects were present, which got annihilated upon annealing, and only that the oxygen went across the columnar grain boundaries, aluminum went out to form the oxide layer thickness. Now, in the presence of silicon, all the V-shaped defects were decorated by silicon, in addition to the formation of chromium silicides along specific defect sites. Now, if you oxidize this film, then we see all the elongated chromium silicides became globular chromium silicides across the grain boundary, and all the V-shaped defects annihilated, silicon came out, and on that silicon now got into the matrix of the max phase, stabilizing it, and therefore enabling aluminum go out of the grain boundary and form the self-healing process of aluminum oxide formation on the surface, which is much thicker, much smaller in size compared to the 0% silicon condition. So now this brings into the context of how can we get information from different microscopy techniques at the nanometer scale to put them together to understand this kind of a mechanism-oriented materials design. So this introduces the concept of correlative microscopy, where we take information from different microscopy technique, for example, chemical mapping here to identify silicide, quantitative analysis by having the line profile, trying to find chromium silicide, combining that with the transmission diffraction, where we try to see that this crystal structure corresponding to silicon enrichment now belongs to a cubic phase of chromium 3 silicide. So you get a crystallography, you get a chemistry, you get the location identification. Now you can now take it to the atom probe tomography in the nanometer scale, do the similar type of a mapping, and see that there are 3 different regions present inside. If you take the tip to the atom probe, then you can see the silicon enrichment nicely visualized. That means you can correlate one-to-one in an ex situ method, but you can also correlate on a direct method where the needle itself is looked for crystallography and looked into chemistry by atom probe. So my final example, therefore, is how is the method of correlative microscopy has been advanced and what we are able to do at IIT Madras to advance this technique to study, for example, the additive manufactured materials, which are the emerging field. So one example there. Now, most of you may be aware there is something called scanning electron microscope, where you have an electron column and there are detectors present inside. This is a conventional stage. If you now want to get the orientation of any sample present inside, you can now tilt the stage by 70 degrees, insert the sample, which is the bulk sample in millimeter or centimeter, enable the electron beam, bombard the sample or interact with the sample, enable the diffraction to happen so that you can get backscattered electrons diffracted. Because the sample is tilted at 70 degree, there is an EBSD detector which collects all the backscattered beam, which is diffracted, and so you see these Kikuchi patterns forming on the surface of the detector. So based on that, now you can get the orientation mapping as the electron beam scans through the surface. This is a very typical conventional electron backscatter diffraction. So what we have done now is From the diffracted information, we know what are the orientation of the grains present inside. We now identify certain specific orientations for much more deeper analysis. That means much more highly resolved nanoscale analysis. So we prepare in a dual beam microscope a very thin segment, as you see here, which is typically 100 nanometer in thickness. At 100 nanometer in thickness, when you now introduce the electron beam similar to conventional microscopy, because the thickness of the sample is very low, this electron beam can penetrate the thickness. That means it is electron transparent, can go through the thickness. And then we insert what is called a stem detector, where you get in the middle a bright field image, and any diffraction that is happening on the sample because of the nanoscale features present inside, you get on this concentric circular detector a dark field image and a high angle dark cloud image, depending on the degree of diffraction that is included. And the most strongly diffracted signals are again collected by this backscatter detector, which is therefore called a transmission Kikuchi diffraction. So that means anything that is passing through the lower part of the sample, subjecting the incoming beam to diffraction, is being collected here. So we can now get the transmission Kikuchi diffraction together with bright field and dark field imaging, all happening on the same analysis volume, which is therefore called the correlative microscopy. So one example of this microscopy, or to put into context, how can we cover all the length scales using this modern day correlative microscopy for nanoscale material analysis. Now imagine you have a component which is in the macrometer scale and that has a microstructure with different grains present everywhere. Now you can do a conventional EBSD to get the orientation mapping of all these grains. You can use the crystal structure to get the information of the phase mapping. And you can also get a chemical composition by doing EDS. But if you now want to see the nanoscale features dissolved, that means there are nanoscale features present inside, but the resolution is limited to 40 to 50 nanometer for a conventional EBSD. Now, if the feature is smaller than 40 nanometer, this is no longer going to be resolved at this scale. So therefore, having seen the feature, if you now take only this region in an electron transparent condition and do the transmission imaging as I showed in the earlier slide. That means for this given volume, we can now be able to resolve more nanoscale features if you go to the nanoscale and do the phase mapping by this transmission Kikuchi diffraction that I showed before. And you can now take this transmission Kikuchi diffraction identified precipitates to the atom probe, and then you can now get an atomic scale distribution of elements present inside these nanoscale features. That means the bulk sample, same region is being analyzed by all the techniques. From each of these regions that are being analyzed, we are now going higher and higher in magnification by preparing samples from the location identified from the earlier analysis, and then extending till the atomic resolution, all happening on the same sample, same region of analysis, and same volume. Therefore, we can correlate all the information of crystal structure, orientation, chemistry coming from the material at the same time. So one example of all of these things is an example of an additively manufactured nickel aluminum bronze. A conventionally cast alloy is going to have all of these different kappa precipitates sitting in a matrix of alpha. Now, if you do this, if you distinguish these precipitates in terms of their morphology, you can see the rosette tape structures are all representing kappa 1 precipitate. You can have lamellar precipitates, all these things. So we skip a little bit. So now we produce this alloy by wire arc additive manufacturing. So this is a wire arc additive manufactured nickel aluminum bronze. Now, because of this varying growth direction as well as varying heat profile, we are not sure whether all these precipitates are forming, which is responsible for strengthening of this material. Now, how do we understand these different types of precipitates which are varying in length scale and also varying in dimension as well as varying in chemistry? So now take the same additive manufactured alloy with varying heat profile. There is a substrate below, there is no substrate on top, so there is a varying heat flow as well. So if you take this X-ray diffraction, you can say what are the phases present inside. Typically now we see BCC and FCC, whereas we are expecting 4 different types of kappa precipitates to form on this material. So you take a smaller volume, go into a TM. Now you see across a grain boundary, there are a lot of precipitates that are being visualized in the TM. So now you want to get the information across the precipitate, then you have to go further higher. So across the grain boundary, if you zoom in further, then you see even tiny nanoscale precipitates are present in addition to this bigger globular precipitate. Now we do not know what is the crystal structure because at that length scale is very hard to a diffraction on a single nanocrystalline precipitate, and therefore the idea of transmission Kikuchi diffraction becomes interesting. So now we did the transmission Kikuchi diffraction on the same sample which is used for TM. That means this region of grain boundary is exactly represented here. Now all of these precipitates surrounding these regions globular are all identified by body-centered cubic crystal structure. These fine-scale precipitates are also identified by the sporadic dots that are present along these differently heat flow regions. Now, from this state, if you take, for example, this globular precipitate and take them into atom probe, then you can now see that globular precipitate big size is made of iron-rich precipitate. The smaller precipitates surrounding them are all in three-dimensionally visualized now as iron-rich nanoscale precipitates present. So this means we can now analyze the same analysis volume of the big precipitate. You can see now the difference between imaging in a TM in a bright field mode and imaging in a STEM, which we have developed in a scanning electron microscope. The same grain boundary, but with same precipitate here, but with much larger field of view. You can see here it's almost 6 microns we can see easily in a single image, whereas in a TM, to resolve the precipitate, we can only see 3 microns. The same entire 6 micron by 6 micron we can now map for orientation. Now all of these precipitates are all ideally mapped, so they can now one-to-one correlate with their position and their orientation information. Now the same entire lamella, which is now mapped for orientation, can also be mapped for the crystal structure. Now you can distinguish the matrix being FCC, which is green color, and all these nanoscale precipitates being body-centered cubic structure. If you now want to get the chemistry of this from that little position, you can now go ahead and do the atom probe. Then you can now identify all these nanoscale and the bigger globular precipitates or iron-rich precipitates. You can quantify them to be iron aluminum rich clusters that are being present inside. So this is the way you can now correlate length scale information from micrometer till a nanometer until you can reach the atomic scale. Now similar correlative analysis has been done for grain boundaries. If you're interested only in setting grain boundaries, you can prepare the grain boundary in the atom probe needle, look at them into TM. Now the grain boundary is here, so we mill away these regions to have this grain boundary here. Do the Kikuchi diffraction on this atom probe needle. Then you can see there are two different phases with a phase boundary in between. Now on that phase boundary, if you take it to atom probe and measure them, then you can see all these different phases, 3 of them can nicely be identified with completely different chemistry, all happening at the nanoscale. So similar analysis we have done on a grain boundary, where you can now see there is a misorientation difference across the atom probe volume. Then you can see at the interface with the grain boundary, you can see carbon and chromium enrichment. So that means by the modern day methods, you can now relate one-to-one directly chemistry and crystallography at the nanometer scale, resolve nanometer features, and resolve defects that are present inside, which is all in nanometer range. So to conclude, now we are moving towards the future microscopy, where we are now embarked on a journey of building this particular microscope, which is called the field ion microscope, so that the same sample before going to atom probe after TKD can now be utilized to image individual atomic positions, as what I shown earlier. All the white dots represent one atomic position. So thanks to the Institute of Eminence funding to IIT Madras, we are now building this microscope ourselves with our own custom design, so that we can now relate all the nanoscale features present in the atom probe with respect to their crystallographic details and the atomic position in 3 dimensions using this field ion microscopy. So with that, I think I'm on time. I'll stop here. Thank you very much for listening almost for 2 hours on this particular topic of nanoscale materials analysis using atom probe tomography. So thank you all. Dr. Srinivasa, I'm done. Yeah.
Thank you very much, sir, for your elaborative explanation on the various advanced characterization techniques, especially about atom probe tomography. So, the various features which are very advantageous when compared to other types of. Currently, we'll look for any questions from the participants. I request the participants to pose their questions from your the lecture, what is discussed so far. So, sir has discussed several techniques with respect to usage of this atom probe tomography. So, how to prepare the samples using a focused ion beam process and some case studies to see the application of this APT, atom probe tomography. Especially
Good
that
evening, sir.
self-healing characteristics. It's very much interesting, sir. With respect to the aerospace applications,
Exactly.
applying various coatings, obtaining the
Yes.
self-healing properties.
Yeah.
Yeah. Somebody is raising question.
Hello.
Yes. Yes. Please
Hello.
go ahead. Yeah.
Yes, please carry.
Yes. You are audible.
Sir, in that self-healing processing, I think you have added silicon, right?
Correct.
Hello.
Yes. Yes. Correct. Correct. We have added silicon
So
intentionally. Go ahead.
silicon is only for accelerating alumina. Is there any specific reason behind that addition of silicon?
No. So we initially produced a coating without silicon, and then we are still able to get alumina on oxidation. But the thickness of alumina was not sufficient enough if you want to claim that the crack is now fully covered by alumina. So therefore, we want to now accelerate the process of alumina formation. At the same time, we do not want the max phase to be disordered. So now if you want to do that, then you need to have certain elements, for example, in the case silicon, to substitute aluminum when the aluminum comes out to react with oxygen. So therefore, we added silicon, which is a group element, with the hope that silicon will replace aluminum when the aluminum comes out for oxidation.
Okay, with that too, up to 1 atomic percent only, right, sir?
Yes. So as I showed before, if you now increase more than 1 atomic percent silicon, we notice that the alumina layer thickness gets thinner compared to a condition with 0.7 or 1 atomic percent silicon. Therefore, we stopped analysis with 1 atomic percent silicon.
Okay.
Any other questions from the participants? And especially with respect to additive manufacturing, you said, sir, it is being characterization technique being used for additive manufacturing. This is especially for nickel, aluminum, bronze materials.
Yeah, I showed an example of nickel, aluminum, bronze, but we do on other materials also, like maraging steel, a lot of different additive manufactured materials, because all additive manufactured materials are in non-equilibrium state. So you can now expect chemical heterogeneity across the volume that is being prepared. And correspondingly, when local variation happens, we can always expect different nanoscale features to be present inside. So more often, unless we do atom probe, we may miss out on the phases present at the coarser level. But for the properties, these nanoscale features are really important.
Yes, sir. Especially for mechanical engineers, this is very much suitable area for research.
Exactly. Yeah.
Any other questions?
Sir,
Yeah.
Sir, good evening, sir.
Yeah, good evening.
Sir, I have one doubt. Sir, mixed of metal ion, how to check that exists the stablest molecule, stablest structure, chemistry point of view?
Okay. The first part of the question was not clearly audible. Can you repeat this again? First part of your question.
All different clusters are stablest structure. How to check that stablest form, sir?
Okay, so anything on a nanometer scale, as I shown 2 examples of clustering, that cannot be considered as stable forever. It is in a metastable state, right? So when we now apply thermal energy for a given time, so these clusters therefore will try to coagulate or coarsen, so that the smaller ones get disappeared, bigger ones tend to coarsen to reduce the free energy of the interface. So this is bound to happen. The only difference is, for any material that is produced in a non-equilibrium way, these kind of nanoscale structures will exist, but it will exist as long as there is enough energy available for them to coarsen. When energy is available, then they are going to coarsen. Now, in the prepared condition, if we now want to know why they are stable, then first thing we have to realize is what is their chemistry, right? Unless we know that this nanoscale feature has certain chemistry, it cannot be stable.
Okay, sir.
Okay. So because
sir, thank you, sir.
With certain chemistry, we get certain crystal structure for a certain size, and that crystal, that size therefore has a orientation relationship with the matrix. Now that orientation at the interface stabilizes this particular nanoscale feature. I hope that answers what you wanted to know.
Okay, sir. Thank you, sir. Thank you for your. Thank you, sir.
I'm also putting your email ID, sir, in the chat box.
Yeah, sure, sir, sure.
So that participants can even email to sir.
Yeah,
So
anytime, no problem.
Undergoing research activity in this area.
So like I said before,
more about the facilities where they are available.
Yeah.
Even sir has explained that how the facilities are useful for Vijayanagar and localites. So you can use the facilities available at Hyderabad also. No, sir.
Yeah. So through ARCA Hyderabad, you can access the facility remotely. Even sitting at your home, you can operate this microscope.
Still any more questions expecting from the participants? I think if there are no more questions, I would like to thank sir. Thank you very much, sir, for sharing your wonderful experience on this atom probe tomography and all other characterization techniques, and comparing all these techniques and explaining how important is this APT useful for characterization of nanoscale materials. Thank you very much, sir, for your valuable experience and expertise shared with to all our participants today. Thank you very much, sir.
So thank you, Dr. Srinivasan, for inviting me for this faculty development program. I hope this information is useful for most of the participants. So if they have any questions, they can feel free to write to us anytime.
Also, I request you, sir, to kindly share the presentation material.
I'll do that. Yes, I'll do that. I'll share the material tonight.
Sure, sir.
And then you can distribute to them. No problem.
Sure, sir. Thank you very much, sir.
Okay, sir. Thank you, sir. Thank you.
Bye-bye. Thank you, sir. Thank you very much. Good night, sir.
Good night. Bye-bye.